Dr. Justin Sanchez is a graduate from the University of Florida in Gainesville with a Bachelor of Science in Engineering Science, and subsequently he had a program in biomechanics, and his doctoral degree is in biomedical engineering. He has received an award for excellence in neuroengineering and an American Epilepsy Society Young Investigator Award in 2005. He's an assistant professor in pediatrics, neuroscience, and biomedical engineering at the University of Florida. And welcome, and we look forward to your talk.
So thank you so much for having me. I really enjoy the opportunity to look at the future and develop new visions for the future. And I'd also like to thank some of the previous speakers for really setting the stage for some of the things that I have to say today. So the title of the talk here is Symbiotic Brain-Machine Interfaces. And I'm going to describe our new system approaches for integrating man and machine in a more symbiotic a way than has been done in the past. So if you could take a minute here to listen to about my past, as was said, I was trained in biomedical engineering, and I really had this vision for translating new neurotechnologies into the clinic. So I made a conscious decision to move over to the Department of Pediatrics. I'm one of two PhD scientists who are really trying to make these dreams realities. So the area that we're working in here is building neurotechnologies for overcoming paralysis. We want to develop direct interfaces that bypass injury and allow for new forms of communication and control via this closed-loop real-time interface. So the interface has a few components here. You basically start by implanting some electrodes in the central nervous system. These could be microwire types of electrodes, which actually go into the tissue. They could be ECOG types of electrodes, which just sit on the surface of the brain and detect more field type of activity. Or these could be EEG types of electrodes that sit directly upon the scalp. In the past, the majority of these interfaces have been considered to be thought translators. You would like to derive the intent of the individual to control either a computer, a wheelchair, or prosthetic arm. I know a lot of the other researchers in this area that I collaborate with, we have a very common vision for the future of these devices, and we really envision them in the activities of daily life. And one common image that is often seen in the literature is this individual here that has some sort of implantable technology in the central nervous system that wirelessly communicates with some wearable types of device that can do neural decoding on it. And this device sends some sort of control commands to a prosthetic limb. Now, what would it really take to bring this conceptual drawing to a reality? We have been working in the area of implantable prosthetics for a few years now. We have an NIH grant to develop an implantable system. And the building blocks really just consist of having a signal sensing system, amplification and pre-processing. The top half of this is really embodied into that implant that goes into the head. And then there's a telemetry system that goes to, let's say, a wearable DSP system that does this interpretation of neural activity, control scheme, and brings feedback to that individual. So in this direction here, this is the conceptual drawing for the implant that we are trying to build. It's roughly, as you can see here, this is a skull of a rat. The entire implant can fit on the top of the skull of the rat, and it's roughly the size of a quarter here. It consists of several key components here that have electrode interface right here, and it is connected via flexible polyimide substrate to an amplifier system and wireless telemetry. And then sandwiched between this whole thing is a battery and a coil for wireless telemetry. Our goal is to send out up to 100 channels of the full bandwidth signal from the brain. Okay, so this is like 25 kilohertz type of data, And the way that we're going to overcome some of the power and bandwidth issues is that we've developed a new asynchronous pulse coding technique for sending this data out. So in the direction of building this implant in my laboratory, we have some of the key components. Just Monday before we left here, we did some experiments. We have this flexible substrate that's sitting on top of the animal's head here. We have an integrated amplifier that's flip chip bonded right now to that substrate. And we've done some preliminary types of recording, and you can see some of these action potentials that are in this recording. So we're making great progress towards this implant, and our next step is to start to integrate some of the wireless telemetry on this device. So in addition to that implantable technology, just linking back to that conceptual drawing, we're building wearable DSPs to do the neural decoding that will translate the intent of the individual. And this is just an example of one of our animals that has a cortical implant here and a wearable DSP that we can link together. So while all of this technology is great, and we're showing proof of concept here, we learned a few things while writing a book entitled Brain-Machine Interface Engineering in the last year here. So we really recognize that these types of technologies, they really are the substrate and the enablers to brain-machine interfaces, but there's a key design problem in these types of devices, and it's really embodied by this statement here. The relationship between the user and the brain-machine interface is inherently lopsided. Okay, so everybody's really been thinking about brain-machine interfaces as simple signal translators. We know that users are intelligent and can use dynamic brain organization and specialization. On the other hand, brain-machine interfaces, again, have been conceived as passive devices that just enact commands. All right, and a lot of this has really stemmed from the fact that these types of neural interfaces and decoders have been developed from a strict kind of electrical engineering signal processing type of perspective. They're input-output types of models. They have difficulty working in novel environments and really adapting to the users. So one of my primary goals for at least the next 5 years here is to really speculate and to envision and design new systems that move laboratory BMIs into a scenario where they're better prepared for the activities of daily life. So where did we start and where are we going and how does all this fit together? So this idea of neural coding, this idea of a thought translator for a brain-machine interface is really developed out of classical neuroscience where people are trying to determine the neural code. The idea of neural coding and decoding is really derived from the idea of giving a stimulus and seeing a neural response and then finding some kind of functional or correlation between those two conditions. And I would like to argue here, at least make a claim here, that the vision for the next generation of brain-machine interfaces is very different than that. And that we should be considering things like antecedents, internal antecedents to behavior, and then the consequences of behavior on our internal and external representation of the world. So we start really with the premise that intelligent behavior arises, okay, from actions of an individual seeking to maximize received reward in a complex and changing world. Now this is a behavioralist type of perspective, right? We all in our daily lives are doing things to kind of bring back the most reward from the environment. I really think that this is a central design principle that we should incorporate into the design of brain-machine interfaces. So if you go into the literature of these types of things, you'll stumble upon the perception-action cycle. And this is really the key area that we are going to be bringing into our new types of neural interfaces. And this perception-action cycle is an adaptive, continuous process of using information to guide a series of goal-directed actions. Okay, so while this is a high-level behavioralist perspective, how could this really be implemented in the next generation of brain-machine interfaces? So this is an artist's cartoon of what one of these devices would look like. And as you can see here, you have a disabled individual. And again, this implantable technology is the enabler. But we really envision these neural interfaces that on the other end, you would have an intelligent assistant working with you in that brain-machine interface. Okay? And provided that this intelligent assistant knows what your goals are, you may be able to engage in a dialogue with that intelligent assistant directly through your brain activity, through your thoughts, right? And this is a kind of a revolutionary approach and vision for how to build brain-machine interfaces. So this is the artist's conceptual drawing. How can we actually do that in practice? So what we developed really was a set of prerequisites for building this symbiosis between man and machine. Okay, and we can ask, what are the prerequisites? In order to have that dialogue between man and machine, you have to have some common things, right? And if you go to look into the literature of goal-directed behavior and optimal decision-making, you find a set of criteria here: representation, valuation, action selection, outcome measures, learning, and then a new one that we added, the idea of co-adaptation. And these prerequisites really, they have different meaning depending upon whether you are the user or you're the neuroprosthetic here. So for example, the user, in terms of representation, this could be brain state. For the neuroprosthetic tool or the decoder, this could be an environmental state. As you can see in this list here, a key component here is that the goals are shared between the user and this neuroprosthetic assistant. Okay? And then we can develop a framework that really incorporates all of these prerequisites. And that's what I'm going to show you next. Okay, so this architecture for building these symbiotic man-machine interactions is really based upon the concept of reinforcement learning, where you have a computer agent. So this is a computational method, a computer agent, that's interacting with the environment. In this environment, this could be the brain of an individual or a rat in the experiments that I'm going to show you next, and then the control of a prosthetic arm or robot. So provided you have access to brain states, common goals or rewards, and you can interact with the environment through a series of actions, you may be able to complete this perception action cycle and really develop this two-way types of communication between the user and the neuroprosthetic. Okay, so part of the theory that goes along with this framework here is again based upon reinforcement learning. And then again, linking back to this idea of neural coding and decoding as is done in traditional neuroscience, rather than this knowledge of the kinematic trajectory and neural activity to find correlations, we only provide a performance score. Okay, this performance score could provide a reward or penalty, but does not directly provide information about how to correct for error. Okay, and to put this in kind of layman's terms here, you really want to find brain states and actions that lead to the most reward. Provided that you start to find these fundamental relationships, you can continuously evolve those relationships over time. Okay, and there's a very well-established theory for doing this. Reinforcement learning is based upon of optimal control theory and Markov decision processes. And this equation at the bottom here really encompasses everything that we need to do. We need to find something called a value function. Okay, and the value function relates actions to states within the system. And you use that value system to maximize the amount of rewards. Okay, so enough theory related to this man-machine symbiosis. How are we actually going to test such a system in vivo? So in my laboratory, we build brain-machine interface systems in behaving animals. And basically what we have here is a behaving rat in an operant conditioning chamber. It's made of plexiglass. This rat can observe an external environment. And in this external environment, we have a robotic arm. And we're trying to mimic what would happen in a scenario where you have a paralyzed individual that's trying to reach and grasp an object. So basically, we give this rat several targets that exist in this external environment. There's one here and there's another one here. And the animal must move this robotic arm from a central starting position all the way out to one or the other target. Okay? So the interesting aspect of all of this is that every 100 milliseconds, this robot is going to update its position based upon the animal's neural activation. And at every new position, the animal must choose one of 26 available actions to him. Okay, so you see each one of these arrows here, forward, back, up, down, left, right. These are all the parameterizations of the cube. You must select the appropriate one that maximizes your probability of trying to get to this target situation. Okay? So that's the experimental setup. This is just an example of what that robotic arm looks like. This is a pre-programmed trajectory, and this rat has not been implanted yet with microelectrodes in its brain. And I just use this to illustrate to you what the system will look like once the animal does go into brain control. Okay? And we're going to see a brain control video in a minute. So, again, well, this equation does not like your Mac. The goal of this entire decoding paradigm is to derive a value function. And we can do this using traditional computational types of techniques. And this neural network here is driven by neural activity. This is brain states. The output of this neural network here are actions. Okay, these are 1 to 27 of those actions: forward, back, left, right, up, down. And this Q function, we're going to estimate over time the value of a particular action. Right? And through interaction with this interface, we're going to find that certain actions are more valuable for getting to a particular target. All right? And again, we use well-established techniques. We use something called temporal difference error. You can't see the equation, but if you just take my word for it that we're using well-known signal processing methods in this case. So the proof that all of this is even feasible will be shown in this video here. So in this particular video, the bottom half of the screen is going to be a top-down view of the animal's behavioral cage. You'll see the animal has microelectrode arrays that are emanating from its head. The top half of the screen is going to be the environmental workspace that the robotic arm is in. The robot position is going to be indicated by a blue light, and the correct target that the animal is trying to navigate this robotic arm to is given by a green light. Okay? So remember, in this scenario here, the rat is generating neural states, and at every 100 milliseconds, this robotic arm is updating its position based upon that neural state. And we must choose the appropriate action that gets us closest to the target. Okay, so let's go ahead and start the video here. So what's quite remarkable is in the bottom of the screen, the rat basically reduces his behavior. They don't really physically move too much. And we'll see he's observing the external environment there. The robotic arm is navigating to this left target here. So this is real-time control, brain control of this robotic arm using this reinforcement learning type of paradigm. What's quite interesting is the animal's going towards the wrong target here and then makes an active correction halfway through the trajectory. All right, so remember, this is a naive animal. This is an animal that's not used to controlling robotic arms in any way. And we have developed a communication channel where this animal can learn to modulate its neural activity with this computer agent in a meaningful way that it can obtain rewards over time. Okay, so while this is a great video proof of how all of this works, let me show you some quantitative metrics for what all of this means. When we talk about symbiosis, this could be kind of a dangerous claim here, right? We're actually meaning that the computer agent and the organism are working together to solve a task. So can we actually show this in some of our models? So we were able to do that. In the top slide here, the x-axis is time, and the y-axis is a cumulative reward, right? How much reward the animal received over time. And what's quite remarkable is that initially, when the animal goes into brain control of the robot, the amount of reward that he got back was not very large. But there's an inflection point where the animal starts getting massive amounts of reward. The slope of that curve starts changing tremendously. So we can ask ourselves, okay, from the computational agent's perspective, what happened? Where is the symbiosis? Where are the changes in that computational agent that really enabled these types of changes to occur? And what we found here, again, this is x-axis is time. The y-axis here is the value of each one of those 27 actions. So you see every curve here corresponds to one of the actions. at the inflection point in the curve, we start seeing much more variation in the value of actions. Okay, so something is occurring through the co-adaptation that's causing certain actions to become more valuable. All right? If we actually look at the change in the parameters of this value function estimator, we see that up until the point of the inflection, there is a large change. There's a lot of adaptation that's going on within the model. And then once rewards start becoming obtained more frequently, the amount of adaptation starts to wane off. And this means that the model is finding valuable types of solutions to this problem and does not need to change anymore. The remarkable aspect of these two changes in the computational agent is that they're also reflected in the neural representation of the brain of the animal. So what I present down here is tuning curves from 3 neurons that we recorded from in this animal. So on the y-axis is firing rate. The x-axis is a particular action. So in each one of these figures, you have left, forward, right, up, and right. And you see that before the inflection point in the curve, you have very strong right representation. Okay, so the firing rate for right is much higher than the firing rates for the representation left, which means that the animal was unable to appropriately trigger left actions to get to the targets. Okay, and that's why his behavioral outcomes were so low. After the inflection point where all of this co-adaptation occurred, you see that there is increased modulation for left and right actions. Okay, so not only did the computational agent start to value left and right actions, but the animal's internal neural representation changed. It was plastic, and it began to represent both of those actions in a meaningful way, and it resulted into improved performance. So we think that this is some real preliminary evidence that symbiosis between man and machine is really feasible for the future using this type of architecture. So some key concepts that I would like to leave with you. I started off this talk with the idea of having implantable, wearable types of hardware for man-machine interfaces, and I really claim to you that's only half the story. If we really want to make meaningful relationships with these machines in a therapeutic type of way, you need a form of symbiosis. You need to be able to dialogue with the machine in a meaningful way. And one of the ways that you can do that is through the sharing of goals. Okay? This is the enabler to this more in-depth and rich dialogue with the machine. And I also claim to you that we need intelligent decoders that assist and co-adapt with the user, right? We are dynamic beings. And if we try to build systems that are static in some way, I think that they're going to be less than optimal. So I think that some of the evidence that I've shown today really shows the proof that this co-adaptation is really meaningful for both entities in this. So the final concept here, I'd like to just look back in history of man-machine interaction. It was said, I think, around the 1960s, implanting tiny machines into the nerves of the heart would make us less human. But today, over 500,000 pacemakers are implanted annually. I really think that we're at the frontier of integrating these machines with the nervous system to restore and enhance function. So I'd just like to thank the team here. We had 3 great graduate students, 2 of them which just graduated, who have been working on this project. And I have a set of collaborators, Jose Principe, Jose Fortes, John Harris, and Toshi Nishida, that I work very closely with on this project. So thank you so much, and if you would like to see all of the glorious details of all of this work, please visit the website. You can see all of our publications. Thank you so much.
Are there some questions, please?
Congratulations, that's very interesting. It seems like you're showing also, as a byproduct, is that brain is plastic.
Yes.
And would you consider using it for stroke recovery, kind of like a physical therapy?
Yes, so it's very interesting that you mentioned this, that we're trying to form some new collaborations with the rehabilitation school at the University of Florida. And we think that these co-adaptive types of interfaces can be used to enhance or augment physical therapy that's given, right? So imagine initially a stroke patient may not have very much functional control. You can give more emphasis to the computational agent to assist, right? And as that person starts to, the individual starts to regain more and more functionality, you can reduce the amount of assistance that's given by that computational agent. So, and you can adapt both of these things in real time. So I really think that for rehabilitation, this is going to be a really important concept for the future.
Very nice work. For that rat experiment, have missed the number. How many electrodes do you use? And is there any minimum number? If possible, how many do you want to use?
Okay, so that's a great question. So this animal that I showed you had 32 electrodes. There were 16 microelectrodes implanted in each hemisphere. Okay, during my PhD studies, I actually investigated this question in quite a lot of detail. Given a neural ensemble recorded from either monkey or human or rat, which fraction of those neurons are really critical for deriving control? Okay, and we found in a variety of scenarios that 30 to 40% of the neurons that we kind of randomly sample from the brain are really involved in control. However, if we are involved in these types of symbiotic relationships, I would like to give the algorithm as much neural substrate as possible. And I think that through training, you may be able to increase that number from 30 or 40% to maybe 80 or 90% through this plastic types of adaptation. Okay, so while I do know the lower limit, the upper limit I think is unlimited. I want as many neurons as possible. So that really poses a big challenge to those that are building new electrodes. How do we get access to large ensembles of neurons chronically from these types of animals or humans?
Any further questions? NASA, as you know, is very involved with human robot or computer interactions. Anticipating a trip to Mars that would take, unless they speed up the vehicles, will take 9 months to get there. Have to hang around a year, take 9 months to get there. That's 3 years interacting with a robotic device or a computer device. And again, the lesson learned from 2001: A Space Odyssey, the bad relationship that developed between Hal and the humans was, I think it was the inflexibility of goal setting by the computer. That is, his idea was totally focused on success and didn't have
that flexibility. That's right.
Well, thank you.
Thank you so much.
Fascinating talk.